All right. Hello, hello. Okay, sounds like it's on. Hey, everyone. I'll let these people get seated. Cool. Hello, everyone. My name is Mike Neuder. I work at the Ethereum Foundation. I'm also a Milady. And today I'll be talking about towards Enshrined proposer-builder separation, which is the project I've been working on over the past few months. Just wanted to shout out the EF folks that are in the crowd and have been helping a ton with this project, as well as the core devs and the Relay community. Like, all of this is a product of our collaboration. So, yeah, quick outline of what I'll be talking about. We'll go through what proposer-builder separation is. We'll talk about MEV-Boost, which is an out-of-protocol implementation of PBS. That's the acronym we typically use to talk about proposer-builder separation. We'll talk about enshrining PBS, which is the process of bringing the actual mechanism into the consensus layer of the protocol. We'll talk about why we want to enshrine it, a few different designs we're discussing, including 2-slot PBS and the payload timeliness committee. And lastly, we'll talk about optimistic relaying, which is an iteration on the current MEV-Boost relays that starts to evolve the mechanism in place to look something like enshrined PBS without all of the overhead of actually bringing it into the consensus layer. So that's what we're going to be going through. I'll start off with just kind of the etymology of PBS. So the first time it was mentioned, I think, was this post in Vitalik from June 2021. And so this was even a year before the merge. And the idea here is that proposers who are the validators selected to propose a block during a slot, these are the proof-of-stake elected validators. And this is supposed to be the decentralized set of the Ethereum protocol. So they should be unsophisticated. They should be able to run on relatively low-powered hardware, kind of at-home stakers we want to be able to support. And this is kind of a different set of people than the builders, who are the participants who are actually capable of constructing the super high-value blocks. And in this context, high-value blocks just means they're able to extract lots of MEV from the blocks. And the reason this is a sophisticated thing is it might involve some complicated simulation, many different arbitrages across pools. It might involve having liquidity on a centralized exchange to be able to do arbitrage there. So these actors are going to have kind of by definition be a lot more sophisticated and have higher requirements for running them. And so the idea is to decouple the two roles of proposing the block and actually constructing the block. And this will allow for more decentralization overall. Because if we didn't kind of formalize this relationship between these two entities, then you could imagine a world where large staking pools have kind of out-of-band relationships with builders because the builders are able to produce better blocks. And in that world, the solo staker, the at-home staker, has no way to essentially earn the same rewards that they would in a pool. So the ultimate goal here is to kind of expose this process of block building and block construction to the everyday at-home staker. Cool. So that was kind of the intro. Quickly, we'll talk about MEV-Boost, which is an out-of-protocol proposer-builder separation implementation. MEV-Boost is built by Flashbots, and it was designed by them and launched with the merge. And the key new entity that's defined here is this relay. So the relay essentially acts as a trust broker or a mutually trusted auctioneer between the proposer and the builder. So there's a few trust assumptions going on. The first is that the builder trusts the relay not to steal their MEV. So a relay will have access to the builder block before the block goes on chain. So the relay could, in theory, copy those transactions, unbundle them, and take away some of the MEV from the builder. So the builder has to trust the relay not to do that. The trust assumption from the proposer is that the relay will provide them a valid header to sign. And the reason for that is the builder sends the full blocks to the relay, but the relay only forwards on the headers of those blocks to the proposers. So the proposer's kind of signing a header sight unseen, and they're trusting that the relay will give them and publish a block that actually ends up on chain because they're signing something that they haven't been able to fully verify. And the way this works is the validators run some sidecar software called MEV-Boost. It's used to interact with the relays. The relays are their own implementations that are running in quite resource-intensive ways. And the builders are kind of isolated from the proposers and only communicate through the relay. And I guess the TLDR of MEV-Boost is that it has massive adoption. Right after the merge, kind of immediately it jumped up to about 90% market share, and now it's up to 95%. So almost all Ethereum blocks are built through the relay and through MEV-Boost in general. And the reason for that is quite simple. It's that proposers who use MEV-Boost will earn a lot more than if they built their blocks locally. And again, this kind of goes back to the fact that extracting MEV is quite a complicated process, and builders are highly specialized at that. So allowing them to do that is something that the proposers want to do because their blocks become more valuable. Cool. Now we can talk about enshrining PBS, and the word enshrining is kind of vague, but really we're just talking about bringing this whole mechanism into the consensus layer. And there's a number of reasons we want to do this. The kind of clearest one is the fact that relays are quite against Ethereum's core values. So there's only about 8 relays that are active in production. Only maybe 4 of them have double-digit block share. So it's really quite a small set of operators that have quite a lot of control over the network. It's also a vector for censorship. So immediately, basically, because the relay executes this auction, they get to decide which blocks qualify as valid in this auction. And what this allows them to do is if a block includes transactions that touch an address that's on the sanctions list, for example, they could just disqualify that block from the auction altogether. And when the OFAC sanctions happened, that's essentially what took place. Some of the relays implemented these kind of ban lists, and any transactions, any blocks that included transactions touching those addresses were censored. And lastly, the trustlessness property is kind of taken away. So because there's only 8 entities, it kind of works today where proposers are able to trust those relays and builders trust the relays too, because there's relatively little overhead in that, and the relay reputation matters a lot in that regard. So yeah, those are some of the issues with the kind of value alignment of relays. Additionally, out-of-protocol software is just painfully brittle. So there's been a few high-profile incidents lately, I would say. The first being the low-carb Crusader attack, where a malicious validator exploited a relay bug, and they were able to essentially steal $20 million worth of a different sandwich bot's liquidity. And that was kind of a relay vulnerability, but it also affected the consensus layer, and so not great. The Chapella bug was an issue with Prism where their externally built block signature generation had a bug in it. So immediately post Chapella, there was some amount of missed slots, mainly because those signatures were all invalid. And additionally, there's just high coordination costs here. So the execution layer clients and the consensus layer clients have a very kind of a very well specified cadence of specs and hard forks and producing software upgrades, whereas the MEV-Boost and the MEV-Boost relay are kind of more ad hoc. They're kind of usually thought of as secondary, like kind of second-class citizens in the overall spec, and as a result, the implementations for the hard forks usually come quite late in the development process and just generally add a lot of overhead to everyone's life. And lastly, relays are just quite expensive. The bar plot on the right shows the cost of running the ultrasound relay. This is kind of the estimated cost for a year's worth of operations, and this is just the infrastructure cost. So it's around 70 to 80,000 euros, and that doesn't include DevOps, any software maintenance, any additional overhead of managing such an important piece of infrastructure. And also, there's just no clear funding model. So the relays currently are operating as pure public utilities. A few of them are being run by companies that are trying to monetize in different ways, but for the most part, it's basically just a money pit, essentially. So yeah, that's kind of motivating why we want to get rid of these relays. And enshrining PBS is just the means to that end. And yeah, I guess I'll go through a few of the designs. So the original design was presented by Vitalik in October 2021, and it's kind of a very simple but clean solution to the problem. And what he proposed is we split one slot of today into 2 slots of this PBS version. And the first slot would have these things called beacon blocks. This is kind of the block that we know and love of today. And it includes a commitment to a builder bid. This is kind of the same as what the relay is doing, just in an actual beacon block. And there's one round of attestations that happens after the beacon block deadline. And then the second block that's produced is this intermediate block, which actually contains the execution block body. So this is the actual list of transactions. This will update the execution layer state. And this will also be attested to by the remainder of the attestation, or of the testing committee for that slot. So in the original post, he proposed that one of the subcommittees votes for the beacon block, while n-1 vote for the intermediate block, but you could partition the testing committee in a number of ways. And the builder block is basically given first-class status in this model because they get full attestation weight on their block. And this is what kind of raises the issue and motivated us to think about different designs, is that the fact that the builder block has basically full rights of a proposer block means that some of the security properties, especially around reorgs, are weakened by this design. So I won't go too much into the details here. There's more on this if you want to talk about it. But yeah, this motivated us to think about alternative designs. And this brought us to the Payload Timeliness Committee. So this is a very fresh design, very much work in progress. So it could very well change in the weeks or months. But yeah, some of the themes are similar, but there's some slight variation to what I described in the 2-slot version. So here we have a consensus layer block. This is exactly as before. It has an execution payload header and a builder bid. And this kind of carved out portion in the bottom half of the block is where the payload will show up. But before that, we have the slot and a testing committee cast their normal LMD ghost votes for the block. So this is exactly as the consensus layer is implemented today. And eventually, the builder is expected to reveal the execution payload. So this is kind of like putting the pieces together of the full block. The builder publishes the payload, and now we have the namesake of the design, which is the Payload Timeliness Committee. We're thinking this could just be a subset of the slot and a testing committee, and they cast attestations basically saying, was the payload published on time or not? And this kind of includes it was valid too. That's like part of the validity check that the Payload Timeliness Committee executes. So the kind of subtlety here is that the payload timeliness votes aren't used in the fork choice rule. They're only used to determine if the CL block has an execution payload or not. And the reason you need these votes at all is because the subsequent block's builder needs to know if the execution state changed through the previous block, like if the list of transactions actually became part of the canonical chain, or if it was an empty block, meaning there was no execution payload, and you should use the previous execution layer state. So that's that's what the kind of difference is between this and the previous design. Cool. So lastly, I wanted to talk about optimistic relaying. So this is kind of a different approach to the whole process of enshrining PBS. And it's saying, okay, let's take advantage of the fact that we already have the relays. There's only 8 relays that exist. We can update their software much easier. We maybe can update some of them while leaving others on other versions. And we can kind of iteratively work towards enshrined PBS by removing some of the relay responsibilities. So if you look at this block submission flow, this is kind of what takes place when a builder sends a block to a relay, and there's essentially a lot of steps involved. The block has to be downloaded, it's validated against the execution layer client, it's published through the consensus layer client, and then it goes to the P2P network. So this is kind of inefficient, and it also relies on the relay doing kind of a lot of tasks. It's a very heavy process. So how can we make this more look like ePBS? We can kind of take the bottom-up approach and start removing some of the responsibilities of the relay. So the first version of this, which we call Optimistic V1, we just kind of cut out the block validity check. So this sounds kind of scary, but we kind of, just by doing this, we can save about 100 to 200 milliseconds of latency. And also, it greatly reduces the cost of running a relay because now all of the block simulations that we had to do previously, we can do either asynchronously or just skip altogether. And we protect the proposers by collateralizing builders. So if a builder ends up sending a block that wins the auction but doesn't result in a block on chain, then the builder collateral is used to repay the proposer. So that's kind of the new version of the trust assumption is we trust that the relay has enough collateral to refund the proposer, even if the builder block wasn't valid and didn't end up on chain. You can take this a step further, and this is what we call optimistic V2. And what we do here is we actually just cut out the block download altogether. So this turns out to be the next part of the bottleneck in terms of network latency. And this saves us an additional 50 or 100 milliseconds of latency. And yeah, the same thing as before, we're still collateralized. So if the block doesn't download ever, then we can use the collateral to refund the proposer in the same way we did before. And I'm running out of time here, so I'll just wrap quickly. The end game of this optimistic relaying thing starts to look a lot more like the payload timeliness committee. So here we have the builder and the proposer interacting directly through the P2P layer. So the builders are sending bids to the P2P, the proposer publishes the signed header, and then the builder publishes the block. And here the only role of the relay is to kind of monitor what's happening in the P2P, in the mempool, and attest basically to the timeliness of different events that took place. And so this makes the relay like extremely lightweight. They just need a view of the mempool, and it makes the relay kind of behave a lot like the payload timeliness committee. So it allows us to use some of the infrastructure to kind of build out the relationship between the builder and the proposer, and then when it's time, we can supplant the relay with the payload timeliness committee and bring it all into the protocol. So that's kind of the long-term merger of the optimistic relaying and the payload timeliness committee. So just wrapping up, we're dependent on MEV-Boost relays. That's bad for these reasons, and EPBS is a way to eliminate that dependency. So the kind of top-down approach is starting at the design, speccing out, and working kind of through the normal all-core devs pipeline. And we're also working on this bottom-up optimistic relay roadmap where we change what the relays do and kind of get closer to what Enshrined PBS should look like. So thank you very much. Happy to take any questions.
So how does the collateral work if you have these MEV rewards that are like 2 million or ridiculously high compared to how much builders are paying now?
Sure, yeah, so for the optimistic relaying, what we do is we check that the builder block, the bid on that block has to be less than the collateral value. So that kind of restricts the set of blocks that are actually handled in this optimistic way. For EPBS, this is kind of difficult because there's only so much collateral you want builders to have to put up, right? One way you could think about this is you could have the builders put up 32 ETH, and then they could get slashed up to that full amount for producing an invalid bid. But yeah, there's other ideas, like you could have a kind of a ZK snark that proves that the builder paid a certain amount through a block without actually revealing the block. But these types of things are more speculative. But yeah, this is exactly like the type of thing we're thinking through, which is like, how do these unconditional payments actually get processed, especially in high MEV regimes? Yeah, great question.
Just raise your hand if you want to ask the question, and we will give you a microphone.
Could you explain a bit how the transition to proof, like what did this landscape look like before proof of stake with the MEV-Boost? How has it changed, and how high a priority do you think this is for the network as a whole?
Sure, yeah. I'll preface this by saying I wasn't actually here before the merge, so, but my understanding of how it worked is there was this software called MEV-Geth, which was the original Flashbot's mining sidecar software, and this allowed mining pools to have bundles sent to them from searchers. And so there was kind of a trusted relationship here, and that also worked because the mining pools have a reputation, and they didn't want to steal searcher bundles, because if they did, then the searchers would no longer send them bundles, and that like immediately reduces their value. So yeah, I think in the proof of work world, it was kind of slightly easier because there was so few block producers relative to the like 600,000 validators in the proof of stake world. But yeah, I think as far as priority goes, the relays are quite unstable currently. There's different discussions going around how to fund them, if some of them might start shutting down, if there's no funding model provided. So I would say it's quite high priority, but I'm a little biased.
Any questions? If no more questions, thank you.